Hello, my name is Petros Papapanagiotou, and I'm a Chancellor's Fellow at the School of Informatics, University of Edinburgh. I'm going to talk to you about the DigiFlow project, which involves a real-world case study of process and data-driven predictive analytics for manufacturing workflows. The project is in the setting of discrete and agile manufacturing, where we have small batches of highly customized jobs and production lots going from machine to machine in the manufacturing floor, and human operators performing discrete tasks to those production lots. The setting involves large variability, where every job has different requirements and specifications, human decision-making and coordination to get things done, specifications that may be incomplete or change as we go through the production flow, unexpected issues that may arise, such as faulty materials or issues with the machines, and incomplete and uncertain information. In this setting, challenge is to produce predictive analytics that can help inform decision-making when it comes to planning and scheduling the jobs in the factory. Now, to give you a slightly better picture of what we dealt with in these case studies, in this setting, jobs and orders are sorted in production lots, which could be a crate of materials such as metal tubes that you see here, or some part that needs to undergo a certain manufacturing process. The process is broken down into individual operations that could last a few hours. For example, 6 to 8 hours was a pretty standard duration for these operations as we saw them in our case studies. These operations could be anything from washing that you see here, milling, cutting, testing, painting, anything that is required in the manufacturing process. They involve machines that are usually grouped together based on their functionality, and they're operated, as I mentioned earlier, by human operators. The production lots have to move from machine to machine based on the requirements of the job, and the move is also performed by human movers that carry the production lots around and may also require specialist equipment, for example, if it is a heavy part. Now, because we have a limited number of machines compared to the number of jobs on the floor at any given point, there has to be some scheduling and prioritization of the operations on each machine so that we can optimize the utilization of the resources and to minimize the delivery times. The scheduling is also typically performed manually by the department head. For this reason, we want to provide useful predictive analytics to inform this decision making when it comes to scheduling the jobs so that the scheduling is optimized. DigiFlow proposes a solution based on workflow management for Industry 4.0, combining workflow modeling and management from business process management techniques with live data coming in from IoT sensors, therefore capturing exactly what's going on in the factory floor. The solution is deployed in a scalable, lightweight manner in a cloud and fog infrastructure. In DigiFlow, we work with two manufacturing partners, a small one in Italy, a larger one in the UK, where we deployed the solution and gathered concrete data from real-world cases to evaluate the system. Now, the methodology of our solution is rather straightforward. First, we map the operations of each manufacturing flow into digital workflow models. We then deploy them into the system so they can be executed and tracked automatically. Then we bring in the IoT sensor data to map the physical activity detected in the factory to the digital workflow. And then we extract useful operational analytics contextualized for each job so that we know what state each job is in, where the delays happened, what remains to happen, and so on. Finally, we can use the digitized models to try and predict how much longer it will take to complete the jobs, the costs, where the delays are expected to happen, and so on. Now, in this talk, we're going to focus on the first and last steps of this methodology. We're going to talk about the formal and expressive models of production flows that we came up with for our case studies, and how we can use these models to perform predictive planning and scheduling using business process simulation. At the core of our process models lies this reserve, move, perform pattern that you see here, capturing the very basic steps that one needs to take to perform an operation as part of manufacturing workflow. First, you need to find an idle machine and reserve it for your operation. Then you need to move the production lot to the location of the machine, and only then you can perform the operation. Now, this looks as a simple visual diagram of this pattern, but it has a formal underpinning in terms of a logical specification of each task. This involves the input resources and requirements for each task to happen, as well as the output resources and effects of the task. We then use inference in this logic, which is called linear logic, to compose these tasks together into complex workflows that are correct by construction. Specifically, we have mathematical guarantees of correctness for two properties: linearity, which means that any resource involved in this workflow is accounted for explicitly. It cannot just disappear into thin air or appear out of nowhere. And the correctness of the execution. So we extract an executable process calculus term that faithfully represents the modeled workflow and allows us to execute it in a way that's free from deadlocks and live locks. Now, once we have the basic reserve, move, perform pattern, we wanted to extend it so that it more accurately captures what happens in the manufacturing floor. And specifically, we captured buffering, which is something very common. Buffering occurs, for example, when you have two production workflows that both require the use of the same machine in the beginning. If we prioritize the second workflow, that means the yellow production lot will come in first, and the red production lot from the first workflow will have to wait until step 4 before it can move to machine A. In the meantime, the blue production lot, which is the other part of the first workflow, can already move to machine B and perform its operation there. The issue here is that as soon as this production lot is finished here, in the typical business process models for manufacturing, it will just be queued until the red production lot catches up and machine C becomes available. In practice, however, there is more that needs to happen, because the production lot cannot just stay here in machine B. It will obstruct the operations happening here. And it can also not move to machine C yet, because it will obstruct any operations happening there. Instead, it is usually moved to this buffering zone. The first manufacturer used some shelves on the side of the manufacturing floor, whereas the second manufacturer used specific locations in the factory that were secure, did not obstruct any other operations. Now, this movement to the buffer zone and back, it requires its own set of resources: a human mover, maybe specialist equipment, as I mentioned, and definitely requires time. So when you're doing predictive scheduling and you're trying to schedule your jobs, this needs to be factored in. And that's what we did. We extended the reserve, move, perform pattern that you saw earlier with two types of buffering. One when you're waiting for a machine to become available, and the other one when you're waiting for the configuration of the machine to be updated appropriately for your particular operation. This may take 2 to 3 hours in some cases. In both cases, we're moving the production lot to the buffer zone. This whole workflow now captures in an expressive way all the fundamental tasks that happen for each operation in the production flow. The next thing you can do is put such operations in a sequence to provide what we call standard operating workflows. For example, the department of the smaller manufacturer that we worked with had 14 of these standard operating workflows, which means that every job that went through that department had to follow one of 14 specific sequences of steps. So there is some configuration and customization in these steps depending on the requirements of the job, but the sequence remains the same for the same type of jobs. Now, our larger manufacturer had more complicated and more variety in their production flows, and this was captured as an assembly tree in their ERP system, where the main assembly was broken down into sub-assemblies, each with its own distinct list sequence of operations. Now, a sub-assembly could also involve a complex part that needs to also be split further down into more sub-assemblies. This is captured in the workflow that you see here, where the job is first split into multiple sub-assemblies, and then the parts are joined together and a new sequence of operations is applied to them. Each operation follows the same reserve, move, perform with buffering, the pattern that I explained earlier, and each sub-assembly follows the same pattern recursively, allowing us to further split it down into more sub-assemblies if required. Now, this pattern is then instantiated as a concrete workflow by mining the appropriate data from the ERP system, where it is already entered as standard practice now. It's readily available for us to construct our digital workflows. Once we have the digital workflows of the operations that need to happen, we want to be able to simulate them to predict how long the jobs will take and so on. To accomplish this, we need to model the environment and resources involved in these operations, including the types of operations available, the locations of the machines, the type and number of machines and equipment available, the configurations for each machine that are changed its functionality based on the operation that needs to happen, the costs of running the machines, material costs, and so on. And of course, because you have human operators, movers, and so on, you have to model their shifts, their breaks, their holidays, etc. Once you have this, the simulator can predict a timeline of operations using heuristic optimization as well to try and optimize how these are planned, and give you a list of interesting predictive analytics, such as costs, delays, and durations, but also rely on the IoT data coming in live based on what's happening in the manufacturing floor. Here we see the sequence of operations predicted for each machine. More importantly, you can predict the total duration of each job, including its delays, so that you can more accurately quote this, for example, as the delivery date for your customer. Now, I wanted to evaluate this prediction of the duration of the job using data from almost 7,000 jobs in 2018 from our larger manufacturer, with an average duration of 56 days. Most of them, 90% of them, were less than 100 days, and a small minority was longer than that, with 1% being even over than 1 year, so very long production processes. Now we use two metrics to try and evaluate the quality of our prediction. First, we extract from the ERP system the start date of each job, the date it was entered in the system and into the factory, and also the actual end date, which is the date marked in the ERP system as the completion of the job. We also extract the manually estimated date that the department head tried to estimate when he entered the job into the ERP system, using their experience and knowledge of how busy the factory is. Finally, we entered all the jobs into the simulator and produced predicted dates based on the optimized schedule from the algorithm, from the simulation, the business process simulation. We then measured the errors for the manual estimated date and the predicted simulated date compared to the actual completion date. The smaller the error, the better the accuracy. We also compared the two errors together to see how much we improved the prediction compared to the manual estimate. In a simple example, if the manual estimate had an error of 4 days and our predicted simulated date had an error of 2 days, then the improvement was 50%. Now, the results in terms of accuracy show that the orange predicted simulated schedule is closer to 0 in all categories, which means that we had a smaller error than the manual schedule. It's also worth noting that the manual schedule always underestimates the duration of the jobs, whereas the simulated schedule sometimes overestimates that duration. I'm going to explain an example next. Here are the results in terms of prediction improvement. For 56% of the jobs, we actually managed to improve the prediction compared to the manual estimate. For more than 25% of the total jobs, we got an improvement of 10%, which may not sound like much, but if you think about the 56 average days in the duration of the jobs, that means that we improved the prediction by a full working week. For 6% of the total jobs, we got an improvement of more than 90%, which means that our predictive algorithm was very accurate in its prediction of the actual completion date. For a small minority of results, we got negative results, which means our prediction was worse than that of the manual estimate. But this involved mainly maintenance jobs that will happen immediately when you manually schedule them, so the manual schedule will be 100% accurate. However, the system did not recognize them as such and queued them as normal operations and grossly overestimated their duration. Finally, we've got roughly 40% of the jobs with the result of 0, which happened because our simulation environment was not adequate to capture all of the particularities of the different operations. For example, when it comes to nesting, you can be cutting from the same sheet of metal multiple parts for multiple jobs, whereas our assumption was that each machine can handle one job at a time. So we've shown that by digitizing the operations into workflow models and introducing a simple resource environment and resource model for the factory, you can get significant predictions and improvement in the scheduling of your jobs. The important thing to note is that even though there is some effort required to build these models, especially in terms of the environment and the resources of the factory, once you can leverage not only the process but also the data that is automatically mined from the ERP systems or passively collected by the IoT sensors, you can maintain this system with minimal intervention, which means that you can continue to get the benefits of the improved scheduling with very little effort. Thank you.